Thank you very much, Rafael. Good afternoon. Let me try to start with a little bit of historical motivation for the contents. This has to do with the dynamics of partially hyperbolic diffeomorphisms, but at the same time, the talk is a little bit more about tools than about results, although I'm going to use one specific result to kind of advertise the tools. And from my point of view, it started quite a long time ago when Christian and also I forgot to mention José Alves were trying to develop a theory of an ergodic theory for partially hyperbolic diffeomorphisms. And what we sort of achieved at that point was, there's several results, but the general idea is what is written there, that if you have a partially hyperbolic diffeomorphism whose central direction is either mostly contracting or mostly expanding, then one can say a lot about the ergodic theory. By that I mean that we could prove that under either of the two assumptions, these maps have a finite number of physical measures, and the basins of attraction of these physical measures cover almost every point. So the asymptotics are well defined. The Birkhoff time averages are well defined almost everywhere. Now, the notions of mostly contracting and mostly expanding were not meant to be definitions. They were more like working conditions. But in at least philosophically, mostly contracting means that all the Lyapunov exponents of the map along the center direction are all negative. That's the general idea for mostly contracting. And that should happen on most points. And whereas mostly expanding, again, philosophically means just the other way around, just the opposite, that all the Lyapunov exponents of the map along the center direction are positive. So that immediately raised several questions. Perhaps one of the trickiest was what happens if you have both expansion and contraction along the center, which we didn't really think so much about. But we did think a little bit about the even more obvious question of what if there are zero exponents along the center direction? What can you do if the exponents happen to vanish along the center direction? And actually, at that point, the question we had in mind was, can we actually avoid having to deal with that? That was our main hope, that we didn't actually have to tackle the problem of vanishing Lyapunov exponents. So we worked a bit on removing zero exponents, and there's a paper of Christian and Alexandre Baraviera that was developed under that spirit. Now, as 13 years later, the point of view has changed, and it's more like instead of trying to avoid zero Lyapunov exponents, we should make them work on our behalf and try to extract information from that. And that is the contents of this statement, which is we called after Artur, Avila, and myself, called the Invariance Principle, which says, this is not a theorem, but there are several theorems with this flavor, and that's why I call it we call it the principle. For Lyapunov exponents of a system to vanish, then something very interesting must be going on. And I will make this statement concrete in examples. It takes different shapes in different situations, but in general, what we realized is that when Lyapunov exponents vanish, the system has a lot of structure that you can try to use to your benefit. Instead of trying to show that this doesn't happen, you just show that it's actually quite special, and you can say a lot about such systems. So there will be a precise theorem that belongs to this family of results under the umbrella of the invariance principle. So a little bit of history. The first version of the invariance principle without the name appeared in Christian and our joint paper with Javier Gomez-Mont, and that was for linear systems, and the base dynamics was hyperbolic. Then with Arthur, we extended the statement for nonlinear systems, again with a hyperbolic base dynamics, and that's where we coined the expression invariance principle. And there's also a paper that is to appear in Astahisk, jointly with Jimmy Santamaria, where again we extended this invariance principle for partially hyperbolic base dynamics, again nonlinear. There's even a more recent preprint, or not even draft, where we extend this further by removing the volume preserving assumption. That's joint with Mauricio Poletti and Elais Malheiro. So this kind of statements has been used by several people in different settings and for different purposes, which hopefully means that this can still be useful in other situations. Okay, so let me move on to the one specific, very concrete situation where you can see the invariance principle at work. And let me stress that what's nice about the invariance principle is that it applies for systems whose hyperbolicity breaks down. Hyperbolicity is good because it gives you a lot of geometric structure, invariant manifolds, and so on. And that's precisely when you don't have that the invariance principle comes to the rescue. Okay, so the setting is this one. I'm going to consider a linear map on the torus, so a linear automorphism of the torus generated by a linear map. And I'm going to assume that this linear map has exactly two eigenvalues on the unit circle. Then there's one eigenvalue whose absolute norm is bigger than 1, another which is smaller than 1. And then there are these two eigenvalues lying on the unit circle. So when you see this as a map on the torus, it's a partially hyperbolic map with one-dimensional unstable direction, one-dimensional stable direction corresponding to the two hyperbolic Lyapunov exponents, and then a two-dimensional center direction that is the eigenspace associated to these two eigenvalues. So I'm going to assume, for reasons that go, somewhat technical reasons, that no one of these eigenvalues is the root of unit. And that has the advantage that corresponds to saying that this linear automorphism is ergodic with respect to the Haar measure on the torus. Now, Federico Rodriguez Hertz proved a much deeper fact, which is that this map is stably ergodic. This is a linear map, and it's not difficult to prove that it's ergodic, but what Federico showed is that if you take any volume-preserving diffeomorphism on the neighborhood of this linear automorphism, then this perturbation is still ergodic with respect to volume. What we prove with Arthur is that such maps are more than just stably ergodic. They are stably Bernoulli, which is a much stronger property. Now, I have to explain that a little bit more because there's an assumption. I'm going to fix any symplectic form on the torus which is invariant under A. With my assumptions, there always is a symplectic form invariant under the map. I choose one, and I fix it once and for all. And then the theorem says that every diffeomorphism F close to A, which is symplectic with respect to this symplectic form, is equivalent to a Bernoulli shift. So every symplectic perturbation of A is Bernoulli. The theorem is quite more detailed than that. It gives a dichotomy. There are two things that may happen. And this is where you see the advantage of the invariance principle. One thing that may happen is that by perturbing your linear automorphism, you move the Lyapunov exponents outside of 0. So you don't know if that happens, but it may happen that by perturbing the diffeomorphism, the two center Lyapunov exponents become non-zero. Because of the symplectic assumption, they are either 0 or either non-zero, both of them. So if that happens, then of course you are in the hyperbolic world, non-uniformly hyperbolic. And as I will comment later on, every non-uniformly hyperbolic volume-preserving diffeomorphism with one additional condition is Bernoulli. So this alternative, hyperbolicity itself, gives you the Bernoulli property more or less for free. But I'm not sure you can always find a perturbation. I'm not saying that. I'm saying I don't have to worry about that. Because if otherwise, in the complementary alternative, otherwise your map F is actually conjugate to the unperturbed linear automorphism. So either you move the exponents outside of 0, or else that's because you actually did not perturb your map at all. That's because your perturbed map is actually conjugate to the original one. The conjugacy is by some volume-preserving diffeomorphism, C infinity diffeomorphism.
Both examples are, so the two cases exist.
The two cases exist, yeah, sure.
Like for dimension 1.
Sure.
No,
Yes. I mean, the theorem answers your question, right? Either your map is C infinity conjugate to the original one, and of course, that's an infinite codimension submanifold in parameter space. Yes, that's C infinity. So a C infinity diffeomorphism. Well, I'm not being very precise at this point about the smoothness of the diffeomorphism, but if you start with something, if you put yourself in the C infinity category, then the conjugacy is C infinity. Or else, your map is non-uniformly hyperbolic. And that's what the theorem says. Okay. Maybe I should say something about smoothness. I'm going to talk about C infinity. In fact, the theorem holds for finite differentiability. I'm stating there that C22 is okay. In fact, our methods only use a couple of derivatives, but Federico needs more derivatives, and 22 is enough for Federico, so it's enough for us as well. Also, the theorem is true in any even dimension, as long as you keep the center two-dimensional. But in higher dimensions, we are not able to prove that the conjugacy is a diffeomorphism. It's only a volume-preserving homeomorphism, which is good enough for Bernoulli, for getting the Bernoulli property. But, I mean, that's what we can do. The methods for proving smoothness of the conjugacy definitely don't go up in dimension. Okay, let me explain how Lyapunov exponents enter into the picture. First a few simple remarks. Every nearby diffeomorphism close to A is partially hyperbolic with an invariant splitting which still has two-dimensional. And Federico proved that all the iterates of F are ergodic. That's part of Federico's thesis. So we look at the Lyapunov exponents of this map. They are numbers because of ergodicity. We have one positive, the two center Lyapunov exponents, and then the stable one, which is strictly negative. And the assumption that the map is symplectic implies that the sum of these two coincides with the sum of the center exponents, and that sum is 0. So there are two cases. Either the center, when you take a nearby diffeomorphism, either the center exponents became non-zero, that is, f is non-uniformly hyperbolic. That, together with the fact that all iterates of f are ergodic, implies that the map is Bernoulli. That's a general fact. There are various versions. The latest complete statement is by Ornstein and Weiss. So that's done. If the exponents become non-zero, then out of general principles, you get the Bernoulli property. So we are left with the second case, which is when, despite the fact that you perturbed your diffeomorphism, the exponents did not move, and they are still zero. Now, what we want to prove in this case is to prove that the diffeomorphism is conjugate to a linear automorphism. So we want to prove that up to change of coordinates on the torus, your map is algebraic. And we do this a little bit the other way around. Instead of proving that the map is algebraic after a change of coordinates, we go looking for the algebraic structure that this map should preserve. We are going to find on the four torus some algebraic structure that the map preserves. And we are going to construct this dynamically. And once that is done, the fact that the map preserves this algebraic structure means that the map is algebraic, and it's conjugate to A. So the way to get this is just an outline of a sort of table of contents of what I'm going to detail next, is that we are going to produce a translation structure on the center leaves of this map. The translation structure, well, let me go to the end of the paragraph and then I explain. Which, as part of obtaining this translation structure, an intermediate step is to obtain a conformal structure on the center leaves. Conformal structure, everyone knows what that is. It's the structure of a Riemann surface. It's to construct an atlas on the center leaves such that the changes of coordinates for this atlas are conformal maps. Translation structure is a stronger version of that. It's an atlas on the manifold such that the coordinate changes are always translations, which of course are very special types of conformal maps. So this is what I'm going to do, but it will take more than one paragraph to get there. Let me explain that. First of all, some general remarks. Every map which is close to A is partially hyperbolic, of course, by robustness, is dynamically coherent, meaning that there are center stable and center unstable foliations, and that follows from general results of Hirsch, Pugh, and Schub, and it's center bunched. By center bunch, I mean this formula here, this inequality. You look at the norm of f along the derivative along the center, divided by the conorm. For A, for the initial map, this would be 1. Now, on this, on the right-hand side, I have 1 over the derivative along S. Since this is a stable direction, this denominator is smaller than 1. I'm taking the inverse, so this number is bigger than 1. And this is the same thing for the n-stable, except that we take the inverse. So both these numbers are bigger than 1. I take the minimum is still bigger than 1. So for A, this inequality is obvious because the left-hand side is 1. By perturbation, this remains true. So this has some interesting consequences. It ensures that if you take 2 points, say on the same stable leaf, and you look at their center directions, their center leaves, well, first of all, so this is the center leaf of Y. First of all, there is a holonomy map taking each point here to the place H, X, Y, S of Z, where the strong stable leaf of Z intersects the center leaf of Y. That's the map that I'm indicating here. It also follows from the analysis that Federico carried out that this map is globally defined. You can take the whole center leaf, and for each point Z, you can find the intersection. There's a unique intersection. And it follows from the center bunching that this holonomy is actually smooth. It's actually C1. It's not much better than C1. It depends on the smoothness, but it is at least C1. So we have global maps defined from each leaf to each leaf, as long as X and Y are on the same stable leaf, that are diffeomorphisms. And these we call the stable holonomies of the map. And in just the same way, by looking at points that are on the same strong unstable leaf, we get the unstable holonomies of our map. Now, the fact that they are differentiable means that I can take the derivative. So there's also a linear map going from the tangent space here to the tangent space here, which is just a derivative of this holonomy. And I'm not so much interested on those maps as on the projective version of those maps, the projectivization. So what I'm saying here is that in this picture, from the projectivization of the center bundle of Z to the projectivization of the center bundle at HX ys of Z, I have this map little h x y s. Well, I should have said here x for coherence, and here y. Existence of these holonomy maps allows us to introduce the machinery of the invariance principle. Now, keep in mind that I'm only dealing with the case where the two exponents are 0. That's an assumption for the next theorem. And the main point in proving the theorem is to prove that the map F cannot be accessible. And the reason is that Federico did a lot of things when the map is not accessible. So I'm going to show that that's the case. So accessibility means that you can go from any point to any point along an SU path, a path that is formed by smooth segments inside stable or unstable leaves, and I'm going to show that that cannot be the case if the exponents are 0. So here is what we get from the invariance principle. If F is accessible, then there exists a family of probability spaces on these projective spaces. On each one of these, we get a measure, a probability measure, mx. This is the first stage for getting an invariant translation structure. First stage is to get an invariant family of probability measures on the projective tangent spaces. These measures are invariant under the dynamics. If you take this projective tangent space and you go to the image, the dynamics takes the measure of x to the measure of f of x. That's the second step, the second statement. These measures are invariant under the holonomies. This map h, x, y, s takes this measure, m of x, and maps it to the measure m of y. Same thing for the unstable holonomies. And then as a consequence, these measures, these probability measures, vary continuously with the point. So basically the invariance principle says that you can, at each point, you can assign a probability measure on projective space, which is a circle. And these measures are invariant under anything that you can think of. The dynamics, the holonomies, both holonomies, and consequently, they depend continuously on the base point. Now, here comes the nice thing. Take the point 0 on the torus. By 0, I mean, of course, the map A has a fixed point at the origin, and that's when you perturb that, the fixed point remains there, maybe a little bit to the side, but you can pretend the fixed point remains at 0. So this is the fixed point for F. Remember, we started with a linear map such that the dynamics along the center was not given by roots of unity. So the dynamics is a rotation, an irrational rotation. When you perturb, that cannot change much. So in particular, you know that the invariant measure on the projective space P of EC0 is close to an irrational rotation, could be rational, but if it's rational, it's a rational number with a large denominator, so it cannot cannot have any invariant measure with an atom. Maybe there are no atoms. If there are atoms, they have small measure. In particular, no atom can have mass bigger than 1/2. Now, the nice thing is that when you have a circle, and this is a beautiful lemma of Douady and Earl, if you have a measure on the circle and it has no atoms of mass bigger than 1/2, then it has a well-defined barycenter, the barycenter of the measure, which is a complex number inside the unit disk. And the way Douady and Earl constructed these barycenters, they are invariant under conformal mappings, etc. So now you know that the measure here doesn't have atoms, so it has a well-defined barycenter. You move this, since your family of measures is invariant under allonomies, and you are assuming that your map is accessible, from 0 you can go anywhere. And if there are no big atoms, no fat atoms here, there are no fat atoms anywhere. So at each point, there's a well-defined barycenter for the measure m of x. So what I'm doing here is assigning to each point, in a nice invariant way, a number that lies inside the unit circle. That's sometimes called a Beltrami differential. And Beltrami differentials define, if you have a Beltrami differential on your surface, it defines a conformal structure on the surface. So, at this point, by Douady and Earl, I know that each center leaf has a conformal structure. Each center leaf is a Riemann surface. You work a little bit more, you have to prove something. The center leaves, in this case, are simply connected. So the Riemann surface is either the plane or the disk, or the hyperbolic disk. You work a little bit more, and you prove that it's the plane. So stage 1, the invariance principle gives you invariant measures on projective space, on the projective center bundles. Stage 2, by calling the help of Douady and Earl, you move this metric, measure theoretical structure into a conformal structure on each one of the center leaves. Of course, the way it was obtained, this construction is invariant under everything. It's continuous. It's invariant under the dynamics. So your diffeomorphism sends each center leaf to another center leaf as a conformal mapping, and it's invariant under the allonomies as well. Now, from the next step is to go from conformal, from showing that the center leaves are Riemann surfaces, into translation structure. I recall that a translation structure is a structure where all changes of local coordinates are translations. One way to visualize what a translation surface is to think of any surface where you know which direction is north. Translations preserve north. Now, to do this, I choose one map, a holomorphic map sending the uniformization, so a holomorphic map sending the complex plane to the, say, the center leaf through the fixed points, through 0. So you are identifying this leaf with the complex plane, so you are introducing, more or less arbitrarily, a translation structure on this leaf. Now, take this translation structure and move it around your torus by using the holonomies. From 0, you can get anywhere because of accessibility. So we just push this translation structure around. There's a little problem, of course. The problem is that you have to check that if you start on this center leaf and you move around by accessibility, and you happen to come back, so this is some path gamma, an SU path. So you have to check that if you go around pushing your translation structure on the torus by these accessibility paths, if you happen to come back, what you get is consistent with the structure that you chose in the beginning. So we have to prove, to show that you can do this pushing around, we have to check that if we take an SU path gamma that happens to come back to the center leaf through the fixed point 0, this, the composition of the holonomy maps preserves the translation structure. In other words, that it is a translation. Now, since my center leaves are already Riemann surfaces, and the conformal structure is preserved by holomorphic map, by the holonomies, this composition is a holomorphic map from the complex plane in disguise of the center leaf through 0 to the complex plane. And we know what are the conformal maps, invertible conformal maps from the complex plane to itself. They are just the affine maps. So to prove that this construction is coherent, I have to prove that A is equal to 1. I have to prove that the holonomy map in this chosen uniformization of the center leaf is a translation. I'm not going to do that, but just giving you a little bit of the trick. What we do is, part of what we do is to prove that when you do this going around and coming back, the distance from the initial point to the final one, this distance is bounded, uniformly bounded, depending only on the path, but not on the point. That is based on the fact that was proven by Federico as well, that the center leaves are at uniformly bounded distance from the center spaces. If you think a little bit, if you think about this for 1 minute, this seems to give immediately the statement. That's not true because there are two distances involved here. One is the distance between points on the center leaves viewed as submanifolds of T4, and the other one is the distance with respect to the conformal complex coordinates that I'm considering there. So you have to be careful about this. You have to work. But anyway, it's one of the things that we proved, that the distance between this and this is bounded. That proves that the absolute value of A is equal to 1. And actually working a little bit more, from there you deduce that it's equal to 1. So at this point, I have on each one of the center leaves the structure of a translation surface. I can say, I have the right to say, this is a translation on my center leaf. And here's how from that, we obtain the conformal structure. This translation structure on center leaves defines an action on the torus. This action It's a C action, but now I'm going to write it as an R2 action, which consists just, what's the action on the torus? Given a vector V and a point on the torus, I just translate the point along its center leaf, translation given by this vector. Tau V sub V is the translation inside the center leaf. So this gives me an R2 action on the torus, all these translations, center translations if you want. And we check that if you take all of these translations, these tau V's are homeomorphisms of T4. If you take the closure of this in the space of homeomorphisms of T4, this is a compact group that acts on T4, and the action is abelian, transitive, and free. Transitive means that if you give me 2 points, I find an element of G that takes this point to this one. And free means essentially that there's only one element of G that does that. So, if you associate to each element of the group a point of T4 by this formula, to take the element of the group and look where it takes the fixed point, where it takes Z. This is a homeomorphism from G to T4. So G is nothing else but the torus reborn as a new group. This is a homeomorphism. You take F twiddle as the conjugate of F acts here on the torus. You bring it back to G using this homeomorphism. Because F commuted with all these translations and so on, this map that you get in this way is a group automorphism. It's an automorphism of the group G. And you check. This is a little calculation. You check that it's actually conjugate. As a group automorphism, it's conjugate to A. So conclusion, F itself is conjugate to A, as I promised. At this point, I only argued that it's conjugate by a homeomorphism.
This is in the case that the exponent was 0, and you use that the accessibility class.
I'm assuming two things, that the exponents are 0 and the map is accessible.
Because I don't remember if it's in the case of Federico, he was using that when the accessibility class is only 1 point, also was conjugate.
Could be.
Yes, I think that Federico had this, either is accessible, because I was wondering a case that you do not have accessibility, that still have 0 Lyapunov exponent. And I think that in Federico,
Yeah, I'm going to use that. Now, let me just recall the logic. I'm assuming two things. For the last 20 minutes, I assume that the exponents were 0 and that F is accessible. And using these two facts, I showed that the map is conjugate to A. Now, the conjugacy, that's also something that we proved, preserves all the invariant foliations. Now, A is not accessible. So by assuming that the exponents are 0 and F is accessible, I proved that F is not accessible. It's a kind of twisted logic, but the twisted logic shows that if the exponents vanish, then F cannot be accessible. Okay? So that's what I'm saying. By assuming both things, I end up conjugating F to A. A is completely integrable. It's not accessible. And so I conclude that F is not accessible either.
but you have the move in this case.
No, I mean, the bad news is that everything you heard in the last 25 minutes doesn't exist.
Yeah, well, this is the point.
This was an argument by contradiction. Okay? So F is not accessible. That's all I got from all this. But it's the heart of the proof.
No, I know, but I said if Federico he proved when it's not accessible, when the conjugacy class is only 1 point, then it's conjugate.
I'm going to yeah, that's precisely what is written there. Now that I know it's not accessible, Federico tells me that F is also topologically conjugate to A. topologically. And he also proves that the sum, these two unstable, the sum of the unstable and stable subspaces is integrable, and the S, the corresponding integral foliation is smooth. Since I'm in the symplectic world, the center is the symplectic orthogonal of the SU bundle, so EC is also the center foliation is also smooth. This the integral foliation of the center bundle is also smooth by that's one of the places where I use the assumption that the map is symplectic. Another thing we show is that the allonomies, that's because of the way these things were constructed, the SU allonomy, this has to be proven, this is another lemma, the SU allonomy preserves the area defined by the symplectic form on the center leaves and vice versa. So I have these two symplectic orthogonals, the SU direction and the C direction. They're both two-dimensional. The symplectic form is non-degenerate on each one of them, so it defines an area on SU leaves, and it also defines an area on center leaves. And these areas, these leaf-wise areas, are preserved by the allonomies of the complementary foliation. So using this fact, we can prove that the conjugacy preserves volume. And that goes in any dimension, but it's only continuous. And then there's a fairly old paper of Katz-Nelson where he showed that linear maps, as I consider, are Bernoulli. My F is being volume-preserving conjugate to a Bernoulli map is also Bernoulli. Yeah. As long as you keep the center two-dimensional, that's crucial. Yeah, that still works because you still have center bunching and so on. What is specific to dimension 4 is this: is the fact that in dimension 4, both unstable and stable are dimension 1, and in dimension 1 there are classical methods for upgrading the regularity of maps. Basically, it goes like this. If you have a smooth measure on the real line, smooth area, and you have a transformation that preserves this smooth measure from the real line to the real line, then the transformation has to be smooth. And that's a very one-dimensional thing. So in here, what we do is we look at the volume measure, we disintegrate along unstable and along stable. The disintegrations are smooth measures because, it's classical fact. We prove that the conjugacy preserves these disintegrations, so the conjugacy is smooth along stable and along unstable. We also prove it's smooth along the center, and then we use Journet's theorem, which says that if you have all these manifolds and all this smoothness along complementary directions, then the map itself in the image space is smooth. This is the one place where one dimension is absolutely crucial, because if you have a map from the plane to the plane that preserves area, it doesn't have to be smooth. In 2 dimensions, this breaks down. Okay, so it's somewhat ironical that the role of the invariance principle in this argument is to be the ground for 25 minutes that at the end I tell you don't exist, because this is a proof by contradiction. But it's nevertheless the heart of the proof. So let me give you, to finish very quickly, another application of the invariance principle that has nothing to do with symplectic diffeomorphisms. It's just to shed a more positive light on the role of the invariance principle in proofs. and also expresses this idea that if your exponents happen to vanish, then something very interesting happens. So this is a different application for error-preserving cocycles. And this will be only 2 slides. So take a skew product map like this. The fiber N is a surface, and I'm assuming that the base dynamics F from M to M is an Augsut. This map is an Augsut. And then assume several things, that F preserves volume, is partially hyperbolic with the vertical bundle as the center direction, is center bunched, accessible, and therefore ergodic. This is a nonlinear map, but even in nonlinear setting, you can define exponents, Lyapunov exponents. This is the largest Lyapunov exponent, and this is the smallest, just the rate of growth of the derivative along the vertical direction. You can replace the product by any fiber bundle over M, whose fiber is the surface. And this is the theorem. If the genus of your surface is bigger than 1, then the Lyapunov exponents cannot vanish. So the topology of the fiber has a say on Lyapunov exponents, which for anyone involved in this business sounds quite surprising, because Lyapunov exponents are very measurable objects. They don't care about continuity. Why should they care about the genus of the surface, the genus of the fiber? But it's still true. And the idea is that if you assume that the exponents vanish, then by using the invariance principle, you construct some structure on the fiber. Again, if the exponents vanish, then the fibers have a lot of structure. The structure that you construct in this case is either a non-vanishing vector field on the fiber, a vector field without zeros, or in some cases, a field of pairs of vector fields. Again, non-vanishing. Now, either of these 2 structures cannot exist outside of the torus or possibly the Klein bottle. So if the genus is bigger than 2, then this cannot happen. Okay. That's all I wanted to say. Thank you.